Hello and welcome everyone to yet another episode of the Reading Club. And in today's episode, I'm going to discuss my submission for the MIP Computational Competition in 2023. Right, so this submission actually won the first prize. So, in this episode, I'm going to describe what the competition was about and what exactly I did to win this competition. Okay, so let's get started. Okay, so I would like to begin with acknowledgments. Right, so of course, first of all, I would like to thank the Google Operation Research team. So these are the people I worked with before I started my PhD from about 2016 to 2020, and these people basically made me a better software engineer. And also I gained a lot of knowledge about solver development while working with them. And the people that I'm currently working with, I will also like to thank them, which is Canada Excellent Researcher, which is Andreas Chair. So this and the people at Polytechnic, including my advisors, Andrea and Guy. So these are the people who I currently work with, and they are basically trying to make me a better researcher. Okay, and finally, I would like to thank the workshop organizers and the competition organizers for organizing this workshop and the competition in the first place. Okay, so let's get started with the actual stuff. Let's start with the competition rules, right? So the idea is that we are supposed to solve 50 instances in a series, one after the other, right? And these instances are very similar to each other, except that some parts are changing, right? So these parts can be like the objective or right hand side or the variable bounds, and one or more of these parts can change. And the idea is that we are supposed to reuse the information that we learned by solving the previous instances. Okay, so we have to solve them in a sequence. We can't look in forward, we can look always backward. So all the instances that we have solved so far, we can collect information from them, but we cannot really see in the forward, for like in the sense that we can't really take information from the instances that we haven't yet solved. Okay, so that's the idea, and we are only supposed to use an open source solver with one thread and 16 GB of RAM, right? So I use skip for this competition, and the performance is scored using time and gap scores. Okay, so if at all I proved optimality, then how much time I used compared to the time limit that was given to me. And if at all I could not prove optimality, then they will basically look at my relative gap. Okay, so that those two things basically make the total score. There is also some penalty if I cannot even produce a single solution. Okay, finally, the weight for a particular instance I is 1 plus 0.1 times I, right? So for weight of the first instance in the series is just 1.1, whereas weight of the 50th instance in this series is 6, right? So the later instances in the series are weighed a lot higher compared to the uh, initial instances, right? So that's the idea, like we want to solve the later instances a lot more faster than the first few instances. Okay, so let's get started with the approach. The first we will look at the primal part. Okay, so primal part is kind of easy, right? So let's say if we have solved a few instances, then we have solutions for those instances, and we can just simply pass around this solution, right? So this solution is feasible if only the objective is changing, and nothing else is changing, right? So in that case, this solution of the previous instance is still feasible. But like in the competition and in the real life, a lot of other things are also changing. So this solution stops being feasible, and so we have to do other stuff, right? So the other stuff that initially, that the next best thing that comes to my mind is that we can consider partial solutions. So not try the entire solution, but like consider a partial solution and then try to complete it, right? So if we have previous solution and if we only consider a part of that solution, then we can try to complete it ourselves. But it's a better idea to just give it this partial solution to the MIP solver itself, right? So a lot of these MIP solvers basically take this kind of partial solutions as hints. They call it partial hints also sometimes. So it's better to give this partial hint to the solver instead of us trying to complete them, because these solvers are like they have like a lot of components that we would not otherwise try, right? So they will try to finish this partial solution before starting their normal solving process. Okay, so that's the idea. Like we want to now give partial solutions, but then how do we consider these partial solutions, right? So that means basically we have to discard some solution values. So the first thing that came to my mind was that we can discard the continuous variables, right? So this is the easy part of the MIP, right? So fixing the integer variables and is basically harder part. Once we have fixed the integer variables, then fixing the continuous variables is not that hard. The MIP solver can just simply solve one linear relaxation and just complete the solution, right? So that already increases the conversion rate. When I say conversion rate, basically like number of times I'm providing a hint and number of times the MIP solver was able to convert it into a feasible solution for the next instance. Okay, so this is like fairly improves the conversion ratio, but it is not yet perfect, right? So the next thing that I did was I considered a bunch of solutions, right? So this is like one solution, but let's say if we have solved more instances in the previously, then we can consider all of those solutions. Okay, and let's say if there is some common part among all these solutions, which is like indicated with the green color, then we can just simply pass around this common part, right? So the idea is that if that part is common across all different solutions, then it is very likely that those variables will take will take those values, and uh, this partial solution is more likely to be converted into a full solution, right? So feasible solution. So that's the idea. And this picture is not really representing how much part is common among the solution, right? So it looks like it's just 1/3 of the solution is common, but if I show you the statistics, it's like a lot more parts are common. Basically, like a lot of variables take the value 0 in a lot in this solution. So a, a very big part is common among all the solutions, right? And this is like kind of inspired from the heuristics that MIP solvers typically use, right? So if you take a look at the rinse or crossover, this kind of heuristics basically do this kind of things. Like so they collect a bunch of solutions that they have already found and then try to fix the variables which are common in them, right? So the same idea, but on a larger scale. So this already improves the conversion ratio, and at this point of time, the ratio was reasonably high. So I didn't really do a lot more things in primal side. So now let's take a look at the dual part, right? So the dual part is more juicy, right? So the more stuff is happening on the dual side. So of course, like we did some stuff in primal, and so now we have some solution to start with, and that basically already improves the solving time. But the real bottleneck is also the dual part, which is like proving optimality, right? So we want to prove this optimality very fast, and so there are two major guidelines about how to go about it, right? So the first is that we want to generate smaller trees, better trees, right? So if we have smaller trees, then we will prove the optimality faster. And the other is that we want to explore these trees faster, right? So these are like the high level guidelines of how we can go about improving the dual, right? So I didn't do everything that can be done under those two guidelines, but I will describe the things that I did under this guidelines, right? So the first trick is basically falling under this generating smaller trees, right? So what is that? So that trick is basically reusing branching information, right? So initially, like we don't know anything about branching when we start, right? So all variables are kind of similar, we don't know what to do, but like once we have solved one instance, then we know a lot of things about branching. So the branching history is available for every variable, and we can just simply pass around, right? So particularly the pseudo cost is kind of something that makes a lot of difference, right? So skip basically stores a lot of different things under variable history. So pseudo cost is one of them, and I actually passed around everything that has been stored in that structure, right? So it also contains variables, inference history and conflict history and VSIDS records and a lot of things. But personally, I think that the pseudo cost was the one that made most of the difference. So initially, I don't know any pseudo cost when I haven't solved any single instance, but once I've solved one instance, then I have received enough number of pseudo cost updates for each variable, so I can just simply pass around that learned pseudo cost, and that already makes the subsequent instance tree smaller, right? So that's the idea, like we want to generate smaller trees. And there is another thing that I did while passing around the pseudocost, right? So pseudocost are basically maintained as like two numbers. So one is the average pseudocost, and the second number is the number of times that we have received the pseudocost updates for that variable, right? So the count basically. And what I did was that I reduced that count to a lower value. I pass around the average pseudocost as it is, but the count is reduced. So in other words, basically what I'm trying to do is I'm trying to tell the solver that these are the pseudocost of the previous instances, but the instance has changed a little bit since then, right? So start with this, but don't stick to it. Like learn, like if you get more updates on the pseudocost, then converge to the actual pseudocost faster, right? So this is in other ways I'm trying to warm start the pseudocost and not exactly reuse the pseudocost as it is, right? So this is not something new. Like people have done this before when they are transferring information across restarts also, right? So the idea is that we only want to warm start the pseudocost and not really pass the actual pseudocost as it is, right? So that's the first trick. The second trick is also related to branching, and I used full strong branching for my first instance. Okay, so this is a bit crazy. Okay, so full strong branching is kind of well known in the community that it's a super slow branching rule, right? So it basically tries to branch on every variable and then selects the one that gives you the most biggest bound improvement, and it takes a lot of time to do that, right? So people don't do this a lot often, but the idea comes from the reliability branching. Okay, so what do people do in reliability branching is that initially the pseudocosts are not trained, like, so they don't have any updates at all, so all of them are zero, and so that's like not reliable for branching, right? So people do strong branching at the beginning of the search tree till they receive some enough number of pseudocost updates. So once they receive, let's say 5-10 pseudocost updates for variables, then they think that okay, now that variable pseudocost is reliable, then I can reuse it for further branching, and I can basically stop doing this strong branching thing. So I just extended this idea, like I did full strong branching for the entire first instance to basically in hope that I will receive even more pseudocost updates, which I will pass around for the subsequent instances. So the first instance, obviously I'm losing, I'm obviously super slow, but for the subsequent instances, my trees are even smaller than before. So basically this is how things work out, and yeah, so you don't have to do like full strong branching outside of the competition. You can still extend this idea for your application. The idea is that we want to make more effort to learn pseudocost better, right? So receive basically more pseudocost updates in the initial few instances, and that can be done by just tuning some parameters of reliability branching. You can say that in the first 5 instances, try to do slightly more strong branching than you usually do, and that should basically translate to what I did, right? Roughly. So this is the first trick, and now let's get back to the broader criteria that we were discussing about dual improvements, which is solving smaller trees and exploring them faster, right? So the second trick basically addresses both of them, that is parameter tuning, right? So it's kind of known that in the community that parameter tuning can actually reduce your solving time by up to 20 to 30% in general, but sometimes a lot more than that. So it's always a good idea to do the parameter tuning, and in my case I want to automate this parameter tuning process, right? So I got some idea, like I used some rules, and that was basically inspired from UCB rule in the reinforcement learning. So let's take a look at how I did it, right? So let's say if I have one parameter, and if I want to tune the values for that, like if I want to select a proper value for that, then this is how I will compute the score for each value, right? So each individual value. So this is, let's say, my final score. It's basically made up of two components, right? So first is the average reward. So I'll try that value and see what is the average reward am I getting. Like I'll try that value a bunch of times and observe the reward. So reward here is basically the total score, right? So it's a time and gap part. So if I'm solving faster and everything, then my rewards are higher, right? So that's the average reward, and that's one part. And the second part is the confidence part, right? So if I've tried this value only once, then I'm not so sure that this average reward is an actual representation of actual reward, right? So that's where the confidence comes in, right? So if I tried it only once, then I'm not confident. So it basically means that this value has more potential than what is represented by the average reward. So I should give it more chances if the score is still low, right? So it basically encourages exploration in this framework. But whereas if I've tried this like say hundreds of times, then I'm pretty confident that I have I'm I'm very very close to the actual reward. So NV is the number of times I have tried that value, right? So in that case, I don't really have to add a lot of confidence part in my score, right? So confidence basically penalty to my score. Okay, so that's the rule, and C is basically just the balance parameter. It basically describes how fast you want to converge, and this is like different from UCV branching rule that I have basically tweaked the confidence part, right? So in UCV branching rule, it's like square root of NV, and they also consider the total number of trials across all values, and I didn't consider all those things because I wanted faster convergence, right? So I only have 50 instances and I wanted to converge by, let's say, uh, you know 10-20 instances. So yeah, this is the modifications that kind of work for me in the competition. So there's one more thing that I modified. So the UCB is that rule basically assumes that the underlying distribution of the reward is not changing, whereas this is not true in our case, right? So the instances can become more difficult as we move along, right? So that difficulty basically can change, right? So initial instances might not be very difficult, but later instances are very difficult. That can happen, and in that case, the average reward is not coming from the same distribution. So what I did was I considered the standard deviation for that, right? So let's say I have one parameter and I have three values, right? So these are the scores, and let's say this one is the best score. So I will obviously consider this, but I will also consider some other value, right, for which the score is within say 1/10 of the standard deviation of the best score. So that way, like if the instance difficulties are changing, then my standard deviation is high. That means I will explore more values, right, before I converge to the final value. So that's the idea, and of course, like you can do different tuning than what I did, right? So that was about parameter tuning, and let's see what all parameters are actually tuned using this framework. I only tuned three parameters, right? So first one was cuts, second one was root cuts. So skip basically distinguishes between those, and these are like on and off parameters I tune. So cuts either on or off, root node cuts either on or off, and that's kind of similar for the other solvers as well. And the third one was solution hints. Okay, so recall the primal part where I was actually providing hints to the solver, and conventionally it is kind of the right thing to do, but sometimes these hints are not useful. Okay, so especially in those cases where like finding a feasible solution is easy, in those cases providing solution doesn't really make a lot of difference. uh, but I even observed that in some series, if I provide hints and if they get converted to a solution, then that was actually hurting the solver in the sense that it was taking longer to prove optimality than it would usually take. So it goes against the conventional wisdom of having a better quality primal solution is always good for the solving process, but MIP solvers are truly black boxes, right? So I don't know what went wrong in those series, but yeah, it's not always a good idea. So I thought like it's better to first explore whether giving hint is a good idea or not, and then if it is good idea, then only just give hints, right? So I only tuned three parameters because I tried tuning more, but it was getting more noisy, so I basically had to stop. If I had more instances, probably I would have tuned more parameters as well. Right. So the idea is that use some sort of framework for tuning these parameters. Okay, so back to the square one where we started. Like we want to explore smaller trees and explore them faster. So the last trick is addressing the second part, which is exploring tree faster, right? So it's kind of a minor optimization in terms of engineering. It's turning off parts that are not performing well, right? So MIP solvers has like a lot of different parts, and they are basically by default on, a lot of them, even though they are not useful for all instances, all series, right? So in our case, we can just simply filter those out. So if there are preprocessor, separators, and primal heuristics that I targeted, and if those things are not touching the model at all, like preprocessor running but not really changing anything in the model, or separators which are just running but not producing any cuts, primal heuristics which are running, and I went even like further for primal heuristic, like even if they are producing primal solutions, but if they are taking too long to produce those primal solutions, then I would turn them off. Like, so all you need to do is basically collect the statistics of this from the solver. Skip basically provides those statistics, and then just list them down and see, just if you just compute the ratio about how much they are changing and how much time they are taking, you'll know where to draw the line. Okay, so that's is something like, if we turn them off, then all the time that is spent in these parts can be given to the branch and bound process, and so you will basically explore your tree faster. Right, so these are all the things that I did, and now let's take a look at the results. Okay, so we'll start with the bound series where the variable bounds are changing. The red lines are my red lines is basically my approach, which is reusing information, and the blue line is the base approach where you do not reuse any information, you just solve every instance from the scratch. Okay, so this is the total score that I'm plotting, and the lower values are better. So clearly I'm doing so much better on all the three instances. The last one is the private instance, which I did not have access to before the competition ended. So yeah, sometimes it can do worse in the beginning because I'm basically doing some exploration of parameters and branching. I'm still learning and all those things. So but later on it always catches up and does better than the base approach. So this was for the bound series. The second one is the objective series where the objective was changing, and same thing, right? So initially sometimes it may not do so well, but it can always do better at the end, right? So this was working for the objective series as well. And yeah, the last one, the one at the bottom, is the private series. The other two I had access to before the competition. Okay, and now let's take a look at the right hand side series where the right hand side was changing. The bottom two instances I did not have access to before competition, and the top two I had access to. So yeah, there are the one at the bottom left is kind of not doing so well early, and then it kind of in the third batch it kind of catches up and like does slightly worse, and by the last batch it is now outperforming, whereas the other three series are kind of doing just as expected. Like, it can do worse in the first couple of batches, but look at the the two on the right hand side, which is like doing better from the beginning, right? And it is doing significantly better at the end. So that's the kind of things that we wanted from reusing information. Okay, and the last series was a right hand side and objective. Both of those things were changing. The left one was public and the right one was private. So the left one, it's like worse in the beginning, then catches up and then does better. On the right, it is like worse in the beginning, catches up and only does like slightly better than the base right at the end, but it is still like worth doing that. Okay, so there was one more component which is called matrix series, which this was not really the part of the competition, and so I never really evaluated during my development process. And this is where I'm like it's kind of confusing whether my approach is working or not, right? So the one on the left, where the reoptimization approach is consistently worse than the base approach. The one on the right, where the reoptimization approach is consistently better than and even significantly better than the base approach. And the bottom one, which was in the private instances, so that's kind of confusing. Like, so it does worse in the beginning, then in the third batch it does like slightly better, and then by the end again it is like slightly worse, and that in series basically even had some numerical issues, right? So that I faced in both the approaches, like base and reoptimization. So it's kind of not clear whether what is better there. So typically it looks like the base approach is better, but overall I'm kind of like it's not clear whether the reoptimization approach is consistently better, just like in the other series, right? So this is like kind of a future areas for research, let's say. I'll obviously explore what can be done to do consistently better on even the cases where metrics and the metrics entries are also changing. Okay, so that is kind of it. So to conclude, basically we learned a lot of different things that we can do on primal and dual side to reuse the information that we have learned from solving the previous instances, right? And some of these tricks you might feel that they are kind of very very specific to the competition, and yes, you're right, they are kind of only applicable in the competition, but it's kind of more like think about F1 races, right? So it's like the competition demands like going all the way to extreme measures. So like I did full strong branching in the first instance, and then I changed that parameter tuning formula to converge super fast and all those things, because like those were the weights, right? So first instance has a weight of 1, last instance has a weight of 6, and so extreme measures were needed. And typically in the practice it is not like that. It is like first instance has a weight of 1, last instance may have a weight of lightly higher, let's say about 1.5, but not crazy high like 6 or something. So yeah, uh, the weights are not that crazy, but like just like in the F1, like people innovate in the F1 races, right? And those innovations eventually get transferred to the regular cars that we use. So similarly, a lot of these ideas are kind of extremes, but a scaled version can be basically used for general instances as well. And that's what I'll be also working on after this competition, and we'll hopefully produce a paper out of it and see what can be done when these measures are even not that extreme. So that's the idea behind this approach. We can hopefully reuse all this information, and hopefully this will be helpful to a lot of different industries where similar problems are getting solved. So let's see. Okay, and so yeah, finally, thank you for watching this video. So if you don't know, I also write a non-technical blog, which is at here, and you are already on the YouTube, so you are already watching on me on the YouTube channel. So yeah, I'll be uploading more videos about the stuff that I read and more technical stuff about MIP solving. So thank you for watching, and if you liked it, so hit the like button, and do share, and if you want to continue receiving my videos, then yeah, hit the subscribe button also, right? So thank you for watching, and see you in the next video. Bye.